Okay, so all right, so let me say a couple of words about the homework for next Friday. First, so this is kind of a fun one, kind of breaking the into fields a little bit. Suppose that if you have K inside of F, these are fields, and U is an element of F that is algebraic over K of odd degree. And what I mean by that is it is the root of a polynomial degree, of an odd degree polynomial that is irreducible, right? So as small as possible. Then show that these two fields are in fact equal. Yeah, and what can you say if U is transcendental over K? Number two, let F be a field. So this is kind of an interesting piece about fields and their multiplicative structure. And in fact, it's one of the things that makes finite fields very important in coding. This. So if you have a field, and let G be a subgroup of the multiplicative group of fields. So you got any fields you want, the rationals, the reals, finite field, whatever. Of course, when you take the field and jerk out the zero, that's a multiplicative group. If you have any finite subgroup of that, it's cyclic. All right, that's actually kind of amazing. So that means if you ever have a finite field and you jerk the zero out, the multiplicative group you have, not only is it abelian, it's in fact cyclic, which is really kind of cool. Show that if F is a finite field, then the product of two non-squares in F is a square in F, right? You don't expect this to happen in general, right? In the rational numbers, 2 is not a square, and 3 is not a square, and 2 times 3 is still in a square, right? But if you have a finite field and you multiply two things that are not square, they become square. And finally, if F is finite, show that every element of F is the sum of two squares, right? Everything can be written as a sum of two squares in a finite field. Number three, suppose F and K are fields, and suppose F is an algebraic extension of K. Show if R is an integral domain that you can somehow sandwich between these two fields where F is algebraic over K, then R itself has to be a field. Right? So we've seen other examples where we put Q inside Q square bracket E inside of Q round bracket E, and of course the middle one's not a field, but if it's an algebraic extension, it has to be. Number four, let K be a field and U and V elements in some field extension of K that are algebraic over K. Show if the degrees of U and V are M and N respectively, then the smallest field that contains K and these two elements, the degree of that over K is less than or equal to M N, and equality holds if the greatest common divisor of M and N is equal to 1. By the way, that's not an if and only if, right? If the greatest common divisor is 1, then you get equality, but sometimes you can get equality even if that's not the case. And finally, the last one's kind of a fun one. We're going to be looking at groups of automorphisms. That's basically what Galois theory is about. But this is kind of a cool problem. Find all automorphisms of the real numbers that fix the rational numbers. There ain't many of them. And, you know, this is a kind of a cool problem, I think, because you might want to start by showing that any automorphism of the reals that fixes Q is continuous, right? You never thought you'd hear that word in this class, but there it is. Okay, any questions? Okay. Okay. Right. Also, let me once again plug the math book. we're going to talk about her award-winning research actually about wind, modeling the wind and climate and things like this. So it should be a very good talk. And also, let me remind you, I will be out of town until Friday of next week, effectively for you all. However, if you email me, I might not respond immediately, but I'll respond fairly quickly. We're going to do class. It looks like it's going to work out at the usual time on Monday and Wednesday. If technology kills me, don't worry, I'll fix it, whatever. I'll get back to you and let you know what to do. I'll be in part of working on research and giving a talk, but if you got any problems, just give me a holler and I should be able to get to you quickly. Okay, any questions? Yes.
Do you have office hours next week?
Not formally, no. So just ask me if you need me or something like that. Okay. Theory. Yeah, and so let me say something. If you're really stuck and you need to talk to me next week, it might have to be. We'll see, they're on Central Time. It might have to be sort of in the later days for you all, right? Either in the early morning, pretty early in the morning, or later in the day. We can do a Zoom meeting or something like that. Okay. So we talked a little bit about transcendental, and a big takeaway from last time is, so let me scribble this over here. If U is transcendental over F, then as far as fields go, there's no distinguishing F of U with rational functions over F, right? That was kind of a big takeaway last time. Here we're going to deal with algebraic stuff. Okay, so suppose you have F as a field extension and you happen to find some element U in F that's algebraic over K, then A actually I don't want this is not and in fact B KU is isomorphic to KX modulo the ideal generated by F of X, where F of X is the minimal polynomial. Where F of X is smallest degree polynomial. Well, and let me make this absolutely clear. For zero polynomial doesn't really have a degree. Such that F of U equals 0. C, if you look at the degree of KU over K, this is equal to N, which is the degree of F of X, where F of X, same notation is up here. And every element so every element in this field extension KU can be written uniquely in the form, let's say K0 plus K1U plus Kn minus 1, U n minus 1 with Ki and flexible. Okay, so let's go over this. So let me point out here that actually pretty much everything in here follows part A, right? So A is really the tool that I will extract first, right? And in fact, yeah, I could say equality here too, this way. Note. Yeah, I'm gonna get this as equality. Certainly, that's more than wouldn't it? Note that KU is always contained in K, because this is sort of speaking loosely, this is polynomials in U, and this is rational functions in U as long as the denominator is not zero, right? So it suffices, and we need to make this observation, KU is quotient field, okay? So it suffices show KU is a field. This is actually similar to an example that I did last time. This is just kind of generalized out. All we have to do is show that KU is in fact a field. Okay. So how are we going to do that? Well, this is actually going to show part B as well. Right. So what I'm going to do is let I'm going to define an ideal of polynomials of K as follows. I is the set G of X and K of X such that G of U is equal to 0. Everybody okay with that? Is it clear to you all that this is in fact an ideal, right? I mean, if you have so sums of two things in this. Clearly, if G of X has U as a root, the negative G of X has U as a root as well, right? And in fact, if K of X is a polynomial, then K of X, G of X, G1 of X, evaluated at U, K of U, G1 of U, which is 0. So this is an ideal. Right. Okay, well, now that we've got that, I'm going to appeal to the structure of this. What kind of ring is this? PID. It's a PID. As KX is a PID, I is generated by some f of x, and f of x is smallest degree non-zero polynomial such that f of u equals 0. And by the way, of course, there's many of these minimal ones, but they all vary by a multiple of something in K, right? F of X is unique if we demand it be mine. Right. So what I mean by that is So for example, that might be f of x, and another possibility for f of x is this. You know, any multiple, any non-zero multiple that is. But if I demand that the leading the leading term have coefficient 1, then it's unique. Everybody clear on that? And so I mean, I can always assume that if I like. So what does this give me? Well, what this means is every non-zero polynomial of which u is a root is divisible by f of x, right? So let me set up the following homomorphism. Consider phi from kx to ku given by phi of g of x is g of u. So this homomorphism is basically plug in u for x, right? This is a surjective ring homomorphism. Right? It's easy to check that this is a ring homomorphism. Surjectivity comes directly from the definition of KU, because by definition, anything in KU is polynomial in U, right? So just pick that polynomial to be the preimage, right? Everybody okay with that? Everybody cool with that? So what is the kernel of P? That's exactly right. Kernel of phi is exactly equal to I, the set of and this is that things. So we have a homomorphism. But in fact, so phi induces an isomorphism. We will say a bar from kx modulo the kernel of phi onto ku. Okay. Almost done. Can somebody justify why KU is a field? Because I've sort of looked like I've lost my mind here, right? Because I've started doing all this business. Remember, what we're trying to do in the first place is show that thing's field, right? You can do this like you can get down and dirty and do some computation, show any non-zero thing has an inverse. That's kind of okay. Actually, you've really kind of put your finger on it. Let me first point out that KU is a domain. It's an integral domain, right? We've already seen that before, because in fact, this is always true. It's a subring of a field. It's got a quotient field. Any subring of field is an integral domain. Everybody okay with that? So what does that mean about the status of the ideal generated by f of x? So you have this thing mod this ideal is an integral domain. So what does that mean about this ideal? Right. So f of x in kx is prime. and non-zero.
Yeah, I think this has to be maximum.
Has to be maximum. That's right. But in a PID, every non-zero prime ideal is maximum. And I'm sure that you might have seen this before, but even if you haven't, let me put it to you this way. If it wasn't maximal, it's contained in a strictly larger prime ideal, which has to also be principal because it's PID. Now you have y divides x, right? Which means that x is not irreducible, right? And one of its factors has to be 1. You can come to the conclusion that this is the entire ring, right? That's fairly show. Hence, that prime ideal f of x is maximal. Ku is a field, and so Ku is equal to exposure field. That's kind of cool. Notice B is porous in A, right? I love that word. Right, it's something that follows from the proof. We actually sort of proved we proved part B along the way, right? Right, because we know that K square bracket is isomorphic to this from that statement there, and these two are equal by part A. Let's tackle the last couple, one of which I erased. The degree of Ku over K is equal to N, right? Well, I can tackle C, and since I apologize for having erased it, but part D said that every element of Ku can be written uniquely as a linear combination of the powers of U from 0 up to N minus 1. Why is this true? Well, this is vector space of K. I claim that 1 U squared U N minus 1 is a spanning set. Well, is a basis for and here, let me point out here that N, using my notations, everybody okay with that? Okay. And that'll do it, right? That'll do it for parts C and D in the following sense. This statement right here will mean that the degree of Ku over K is equal to N. So that will establish that for us. And it will also establish the fact that every element of Ku can be written as a K-linear combination of these uniquely because it's a basis, right? So how do we show its basis? Well, two things, right? I need linear independence and I need span. So how about linear independence? Suppose that K0 plus K1 plus K2 U squared plus Kn minus 1 UN minus 1 is equal to 0. And let's suppose, just for giggles, that f of x is a0 plus a1x plus a n x n with a n not equal to 0. Because remember, f of x is honest to goodness degree n, so that means the leading term is not 0. Anybody tell me what's the matter with this? Okay, there we go. Right. This statement right here means that u is a root of polynomial, say k of x is k0 plus k1x plus kn minus 1 x n minus 1. Right? But this degree if any ki is not 0, then degree of k of x is strictly less than the degree of f of x. And this is a contradiction because f of x is minimal polynomial. Forgive it. Right. So we can only conclude that that polynomial that I have written out there is in fact a 0 polynomial. K of x is identically 0, therefore ki 0 for all I between 1 and -1. So the set 1 u squared un minus 1 is linearly independent. How about spanning? Why does it span? Any ideas? Once again, I think the way that I think to do it is sort of use probably ideas. What is a typical element? Let me call it alpha b a. I'm going to use ku in case round brackets used synonymously, right, after what we proved in parts A and B. Well, I don't know much, but I know that alpha is, if nothing else, of the form k0 plus k1u plus km u. Now, let k of x, and let me, of course, first notice that if m is less than or equal to n minus 1, we're already done, right? And the only concern is if this is size n or bigger, right? Let k of x be this part. Okay. Now, I want to compare this with f of x. The greatest common divisor of kx and f of x what can you say about this? Well, let me also point out that if f of x actually divides k of x, then k of x equals g of x times f of x. And so ku equals gu fu, which by the way is alpha, right? Because ku is alpha, right? If f of x divides k of x, what does that mean about alpha?
Zero.
You're correct, it's zero, because this piece right here is zero. And so I can write alpha equals zero. And so I can write it as the all coefficients being zero and certainly staying by the same. Everybody okay with that? On the other hand, what happens if f of x does not divide k of x? What can you say about the GCD? Well, so the GCD has degree less than n. So either f of x divides it, and in fact f of x itself is the greatest common divisor. If f does not completely divide it, the greatest common divisor must divide f of x, and so must be of lower degree. Oh, well, actually, that's an excellent point. Yeah, she's right. I mean, in a certain sense, well, you've also got right, and of course k of x as well, but yeah, you're right. But let me okay, so the greatest common divisor has degree less than n. Everybody okay with that? And what else do you know? Oh, I don't remember what I was trying to get out. How do I know the greatest common divisor? So I'm throwing all this greatest common divisor stuff. How do I know the greatest common divisor exists? Right, there's certainly rings out there that I can give you two elements. There's no greatest common divisor. It's PID. KX is a PID, and in fact, in any UFD, greatest common divisors exist, right? Because all you have to do is pull off the prime factors in common, right? So here, what we have is the greatest common divisor exists. And what else do you know about greatest common divisors and PIDs? Well, actually, right. All of one x. The greatest common divisor is a linear combination of things. Right. And in fact, actually, the greatest common divisor here, right, if k of x is not f of x, it should be 1, right? So, can anybody tell me how to finish this? Yeah.
So how do you know it's one?
Because remember, f of x Remember that? So this is in fact prime identical, right? And so if K of X is not equal to F of X up to a unit, then because think of this like a unique factorization domain. This is a prime, right? And so the only way, so either F of X divides K of X, or if not, if it doesn't, that means K of X has no factors of prime F of X in it, and so the greatest common product has one. Right. Okay. Okay. By the way, it also, we can actually also use this to show this field. But let's get back to it. How do I now use this to show that that this degree is or that one U is a one U squared UN minus one spans. Any
This.
what's it?
So that became like the K of X. Like instead of K of X, use the L of X, and it's lower.
Right, right. But so what we need to So here what we have is we have our element alpha. Right. Now, as we pointed out, at the beginning, m was less than or equal to n, or I'm sorry, strictly less than n, we're done. What happens if this is a degree more? The idea is actually this. Actually, I'm gonna put a little extra oomph in this, right? So we've already got this linearly independent spanning. What about what can you do in f of x is this? My bad. So we've given a lot of lip service to the fact that kx is a PID, but it's actually something even stronger than that. Anybody know? It's Euclidean. We can do the division algorithm. So here's the quickest way to do this. Divide k of x by f of x. There we go. I shouldn't have been messing with the PID case. K of x is divided by f of x with quotient q, and that's the remainder, right? What can you say? When you divide k of x by f of x, you either get d of x equals 0, so you've got complete division, or what? I agree with that. So K of X. This means that K of U equals QU FU plus D. Agree? So this element KU, which is alpha, is this. But what can you say about this element right here, this chunk right here? It is zero. And so notice that du is zero. Either du is zero, in which case clearly it's spanned by the power of u, or du is d0 plus d1u plus dn minus 1 un minus 1, where the di's are in. Okay. So here, this du is my alternative to expressing it as lower powers. Okay, any questions on that? Any questions on that? Let me point out something interesting. I think it's all this. I'm going to start with the base field here of Q. And let f of x equal x fifth minus 2. Okay, I'm appealing to earlier knowledge, but how many roots does that have? Complex roots. You got complete freedom. It should have 5 complex roots, right? Is it the roots of this are 2 to the 1/5, right? Does anybody know what the other ones look like? You ought to try to figure out the roots of this by hand, just for fun. I'm going to write the other 4 down. To 1/5. Omega squared. To 1/5. Omega cubed. To 1/5. Omega 4. Where omega is e 2 pi over 5. Right. These are the 4 complex roots, and I don't know if y'all have seen this one, but the omegas look like this. Oh, by the way, folks, before I forget, I've got a meeting with the chair today at 10:30. So it shouldn't be more than a half hour, but again, come talk to me if you want to come see me. And I will be available this afternoon if you need me. So that time's good for it. So the 5 complex roots of unity basically show up every 72 degrees or so, like this. Two pi over 5, 4 pi over 5, 6 pi over 5, 8 pi over 5, and back to 1. How many of you have seen this where you do this kind of thing on the circle? If you have a really good trig course, you might be lucky enough to have even seen it a long time ago. Notice that these 2 are complex conjugates of each other, right? And these 2 are complex conjugates of each other, right? Now notice this has 1 real root and 4 complex roots that are not real. But notice that if let's say alpha is any of these roots, then Q is going with alpha, it's isomorphic to QX modulo x5 minus 2. That ideal. Agree? So in other words, for example, these two fields are isomorphic. They're both roots of the same irreducible polynomial over Q. So they're isomorphic fields here. So from that algebraic point of view, you can't tell them apart, but it is interesting, isn't it? Because this field is a subfield of the real numbers. This one's contained inside the real number, where this one is not, right? This one's kind of squirming around. It's not inside the real numbers at all, right? Even though these two fields are isomorphic, one of them is, as a number theorist would say, totally real, and the other one is not. So here's any questions on that? So here's a theorem that's kind of in line with this, so to speak. Suppose you have an isomorphism of fields. Whatever this one is, 819. K to L being isomorphism of fields. Fields. U in an extension field, okay, and B in an extension field of L. Then this isomorphism of fields extends to then extends to an isomorphism of the fields KULV. Such that and this isomorphism takes use to be if one of the following hold. Well, let's get either. U is transcendental. Over K, and B is transcendental over L. That part shouldn't be too much of a surprise, because if this is transcendental over K and this is transcendental over L, then this is basically rational functions over K and rational functions over L, and you just map the variables to each other. Or U is a root of K of X, and B is a root of and let me just clarify what I mean by that, because actually that's kind of sloppy notation, because actually the original isomorphism is only defined on the base field. So by but I think this is defined in an obvious way. This is So what I mean by that polynomial under that image is you just use this original isomorphism to change the coefficients of ring K to new coefficients in L. Okay. Any questions on that? Questions on that? I think this is an appropriate place to wrap it up for today. Keep math club in mind this afternoon. And y'all have a good weekend. Oh, Socrates, do you have any questions?
I think I'm fine. Thank you very much.
Okay.